Today we're going to talk about chi-square test for independence. A test comparing the distribution of counts for two or more groups on the same categorical variable is called a chi-square test of homogeneity. A test of homogeneity is actually the generalization of the two-proportion z-test. The statistic that we calculate for this test is identical to the chi-square statistic for goodness of fit. In this test, however, we ask whether choices have changed. The expected counts are found directly from the data, and we have different degrees of freedom. The assumptions and conditions are the same as for the chi-square goodness of fit test. The data must be counts for the randomization condition. As long as we don't want to generalize, we don't have to check this condition. And the expected count in each cell must be at least 5. To find the expected counts, we multiply the row total by the column total and divide by the grand total. We calculate the chi-square statistic as we did in the goodness of fit test. Chi-squared equals the sum of observed minus expected squared divided by expected. In this situation, we have r minus 1 times c minus 1 degrees of freedom, where r is the number of rows and c is the number of columns. We'll need the degrees of freedom to find the p-value for the chi-squared statistic. Let's take an example. A researcher wishes to test whether the proportion of college students who smoke is the same in 4 different colleges. She randomly selects 100 students from each college and records the number that smoke. The results are shown below. Are the proportions of students smoking the same for all 4 colleges? Alright, first thing we need to do is create our expected counts. So, for this cell, the college A that smoke, to find that expected count, we take the row total times the column total and divide by the grand total. And we'll get 22. It turns out we're going to get 22 for all the smokes. For the don't smoke, and it turns out in this particular case that all the don't smoke come out with an expected of 78. Usually that doesn't happen. So what I've done is I've combined the two tables. I have the observed in black and the expected in red. So step 1, our hypothesis. So this is a chi-square test for homogeneity. Null is the proportion of students smoking is the same for all 4 colleges. And the alternative is the proportion of students smoking is different for all 4 colleges. Checking our assumptions and conditions. We're going to have to assume a simple random sample. We are working with counts, and all the expected counts are greater than or equal to 5. Calculating the test. We have a chi-square. And again, I'm just going to do the first and last. The first one's going to be 17 minus 22, the observed minus the expected. Square it divided by the expected. Plus, and then the last one is 66 minus 78 squared divided by 78. Turns out you're going to get a chi-square of 17.23. Drawing my chi-square distribution, my degree of freedom is going to be 3. There are 2 rows and 4 columns. So 2 minus 1 times 4 minus 1 will give me 3 for a degree of freedom. So with a chi-square of 17.23 and a degree of freedom of 3, my p-value is going to be 0.0005. Assuming an alpha of 0.05, the p-value is less than alpha, we reject the claim that the proportion of students smoking is the same for all 4 colleges. Independence. Contingency tables categorize counts on 2 or more variables so that we can see whether the distribution of counts on one variable is contingent on the other. A test of whether the 2 categorical variables are independent examines the distribution of the counts for one group of individuals classified according to both variables in a contingency table. Chi-square test of independence uses the same calculation as the test of homogeneity. We still need counts and enough data so that the expected counts are at least 5 in each cell. If we're interested in the independence of variables, we usually want to generalize from the data to some population. In that case, we need to check that the data are a representative random sample from that population. Let's take an example. The table below shows the age and favorite type of music of 668 randomly selected people. Our age and preferred music type associated. First thing we're going to do is create our expected counts. So our expected counts, to get this 64.77, we take the row total times the column total divided by the grand total, and we get 64.77. And I did that for all the cells. Combining the two tables, I have the observed in black, the expected in red. So our hypothesis, this is a chi-square test for independence. The null is age and preferred music type are independent, and our alternative is age and preferred music type are dependent. Checking our assumptions. Simple random sample is assumed. We are working with counts, and all expected counts are greater than or equal to 5. Calculating our test. Our chi-square. For the first cell, it's going to be 50 minus 64.77 squared divided by 64.77. Our last cell, 77 minus 75.76 squared divided by 75.76. Adding up all the cells, we're going to get 12.95. So here's our chi-square. Our degree of freedom is going to be 4, since there are 3 rows and 3 columns. 3 minus 1 times 3 minus 1 will give me 4. So with a degree of freedom of 4 and a chi-square of 12.95, my p-value is 0.012. Assuming a alpha of 0.05, my p-value is less than alpha, we reject the claim that age and preferred music type are independent of each other. In other words, we're basically saying that they are dependent. Chi-square tests are common, and tests for independence are especially widespread. We need to remember that a small p-value is not proof of causation. Since the chi-square test for independence treats the two variables symmetrically, we cannot differentiate the direction of any possible causation even if it existed. And there's never any way to eliminate the possibility that a lurking variable is responsible for the lack of independence. In some ways, a failure of independence between two categorical variables is less impressive than a strong, consistent, linear association between quantitative variables. Two categorical variables can fail the test of independence in many ways. Examining the standardized residuals can help you think about the underlying patterns. What have we learned? We've learned how to test hypotheses about categorical variables. All 3 methods we examined look at counts of data in categories and rely on chi-square models. A goodness of fit test compares the observed distribution of a single categorical variable to an expected distribution based on theory or model. A test of homogeneity compares the distribution of several groups for the same categorical variable. And tests of independence examines counts from a single group for evidence of an association between two categorical variables. Mechanically, these tests are almost identical. While the tests appear to be one-sided, conceptually they are many-sided, because there are many ways that the data can deviate significantly from what we hypothesize. When we reject the null hypothesis, we know to examine standardized residuals to better understand the patterns in the data.